Welcome to the Backend Grip. Today, we're going to talk about how computers execute instructions. And personally, I think this is so important because once you know how computers execute instructions, then you pretty much know on the low level side how things work, and nothing seems to be magical anymore. Let's look at the components in the computer. So we have the CPU here, which is the brain of the computer, does all the execution. We have the memory area that usually contains the RAM and ROM. And then we have the IO devices area that helps us interact with the outside world. So, having said that, the CPU generally uses this mode to execute instruction. It's called the fetch, decode, execute cycle. And it starts by fetching the instruction by setting the address on the address bus. And the program counter keeps track of this address. So every CPU comes with the initial address. So every time a reset is done, so for example, if you switch off your CPU and then your computer and you start it up, it gets it always starts from this initial address set in the CPU. And what computer manufacturers do is that they set usually what they do is that they set the ROM um, at this address. So still on the fetch um, still on the fetch step in the execution cycle. So we set this value on the address bus, the decoder does its job, and then it routes that value to the right component. And for the initial address value, like I said, it's usually routed to the ROM where the firmware is. So address is routed to the ROM. A signal is set on the control bus that says, hey, I want to read the instruction at this address. And that data is loaded on the address bus. And once that happens, then the decoding step takes place. And now, so the CPU gets the information on data bus and it routes it to the right circuit for execution. Now in the CPU, we have also a couple of components. We have things like the cache, the different types of cache. There's the L1, L2, and in some modern CPUs, there's also even the L3 cache nowadays. We have things like the registers where we can store values while we are computing or executing an instruction. We also have some units on the CPU that actually does the calculation, like the ALU, which is the arithmetic logic unit, and we have like the control units and a couple of components in there in the CPU. We're not going to go into like the details in the CPU because this is out of scope for this video. We're just going to focus on how the CPU does the whole execution, like the flow of how it executes instructions. So every CPU usually comes with instruction set, and this instruction set helps you to know what instructions the CPU can actually do. And so for this sample CPU that we have here, we are let's imagine that we have the CPU that has a 6 bit instruction, 6 bit for instruction. So if we have 6 bits for instructions, it means we can have 2 raised to power 6 possible instructions on our CPU. So I just added a couple of popular instructions that you would usually find on a CPU instruction set. So like, for example, the load instruction to load piece of data from memory, or to store piece of data to memory, or to add immediate value or subtract immediate value, and so forth. You could have a couple more instructions there. Now let's look at a very concrete example. So I just got this instruction online, and for this instruction, this is a 32-bit CPU that wants to perform an addition with an immediate value. So this immediate value usually is part of the instruction. So let's see this as an instruction. So one thing I didn't mention is that this line here is not a single line. So the data bus determines the size of the computer. So if you have a data bus that has 16-bit bus, a 16-bit data bus, then it means it's a 16-bit computer. If it has 32-bit data bus and 32 lines, then it's a 32-bit computer, and the same for 64. And what this means is that when data is loaded onto data bus, we have 16, if it's a 16-bit computer, we have 16 values loaded at once on the data bus. And if it's 32 bits, it means we have 32 bits data loaded at once. And this data we're talking about can only be 0 or 1. It's pretty much a wire. So a wire can only exist in 2 states. It's either it's on or it's off. And yeah, so that's it. So for this sample instruction, it's a 32-bit instruction. So the first instruction, let's assume that's loaded from ROM. Let's assume it's this instruction, and we have this 32 bits loaded on the data bus. And so the CPU does the decode, gets into the decode phase, and it interprets, gets the first 6 bits and says, oh, you're trying to do an addition on an immediate value. And so it gets the value at address 1 by doing the fetch, decode, execute cycle again. So it sets the address 1 value on the address bus. It wants to fetch this value, so it sends a read signal on the control bus that reads the value. Usually, let's say the value is in RAM. So the address 1 gets routed to the RAM. Read signal to read the value from the RAM. Then the value gets loaded on the data bus. The CPU gets this value, and now it has the value at the address 1 and also has the value, the immediate value. It does the addition. So now we are at the execution step. It does the addition, and it now needs to store the value at address 2. And so it again jumps back to the fetch, decode, execute cycle. And so it sets the value, the address 2 value on the address bus, which again gets routed to the RAM. So the value at address 2, so address 2 on the RAM gets activated, and then a signal on the control bus is set to write. But this time it writes the data from the result from the addition onto the data bus, and so that value is set in RAM. And then now we have the execution complete for that instruction. And so the next instruction happens, and usually the program counter just increments by 1 to go to the next instruction, and then does the next thing and the next thing and the next thing following the fetch, decode, execute cycle. So it's also possible to jump between instructions. So instead of going sequentially from top to bottom by incrementing the program counter by 1, it's also possible that you receive an instruction that actually jumps from one address value to another address value and not incrementing. You get what I mean? And that usually happens when you have conditional statements in your program, or also in cases where you're handing over execution from ROM to RAM, usually by the operating system that you have running on your computer. So in a nutshell, that's how the CPU executes instructions. And now let's quickly talk about I/O devices. So after executing instructions, most times the CPU wants to communicate with the outside world. It wants to store information, it wants to send information from itself to a different computer through a network. And the computer needs to do this by interacting with I/O devices connected to it. And in the past, the computers, the CPU usually used the fetch, decode, execute cycle for every byte that it sends to an I/O device. And this made the CPU very inefficient because it spent a lot of time doing this very boring, mundane stuff. And so and the engineers, like the CPU manufacturers, found a way to solve this problem by introducing a component called the DMA. So the DMA stands for direct memory access. And so now, instead of the CPU doing the fetch, decode, execute cycle for I/O communication, it just sets the address that gets routed to the I/O device that it wants to communicate to, and then sets specific signals on the control bus to the I/O device to do the specific instructions, like, for example, to read a block of data from RAM or to write a block of data to RAM. And when it's done doing this, or while it's doing this, the CPU can actually, do other stuff and perform other operations while the I/O device is interacting with the RAM. And once the I/O device is done, once it fetches all the data or once it writes all the data to RAM, it usually sends like an interrupt signal to the CPU to tell it that, hey, I'm done writing all the data to RAM, or I'm done reading all the data from RAM. So you can, round up the I/O operation. And so the CPU stops and pauses what it's doing, saves the information, the current, the state somewhere internally in registers, and rounds up the I/O operation. And once that operation is done, it resumes the operation it was doing before the interrupt. And so that's pretty much how the CPU executes instructions. If you have questions, or if you have better ways of explaining this, to add to this knowledge, then you can write in the comment section. That would be very, very much appreciated. Thank you for watching, and see you soon.